Welcome to today's session. In this session, we're going to look at mechanics, which is the first topic, and we're going to focus on measurements and units. Okay. So we'll look at measurements and units. Okay. We'll look at measurements and units. Alright. So most of the things in physics, they're usually measured. And once you are measured, you must know the unit of that measurement. For example, if this is a land, then you want to know the dimension of this length. You can measure it. Let's say the dimension is 40 meters. That is the length. So the length is 40. So this 40 is just the magnitude. Now you can't know, or we can't know what you're talking about if you just say 40. The house is 40. What is it about 40? Is it 40 in length? Like, is it centimeters? Is it 40 in grams? What is it? What is it we're talking about? Even in man, you can't say, I have 40. You need to specify, I have 40 kwacha. So that is a unit of carryings. So same applies to measurement. You need to specify whether it's 40 meters, whether you're talking about maybe the mass is maybe 2 kg. So specification is very important when dealing with measurement and unit. So this is what we want to learn. Now, there are what are known as physical quantities under measurement. Okay? We have what are known as physical quantities. Okay? What are physical quantities? Physical quantities are just measured quantities. Okay? They're just quantities which can be measured. Okay. They're just quantities which can be measured. Those are what are known as physical quantities. Just a minute, please. Okay. Right, thanks for the patience. So those are known as physical quantities. Quantities which can only be measured. So these physical quantities, they are of two types. Okay, we have what are known as types of physical quantities. We have what are known as fundamental quantities. Fundamental. The other name for fundamental is basic. Okay. So fundamental quantities or basic quantities, these cannot be expressed in any other terms of other quantities. Okay, these ones cannot be expressed in terms of other quantities. in terms of others. Okay, those are fundamental quantities. Now let's look at examples. So these quantities include quantities like mass, quantities like length, quantities like time, okay. So all these are fundamental quantities. Mass is measured in kilograms, length, the SI unit is meters, time, seconds. Okay. Now let's look at derived quantities. This will be the second type, derived. From its term, we can even know derived, meaning that they are just gotten from other quantities. And what are those other quantities? They are just fundamental quantities. So these can be expressed in terms of other quantities. Okay, this can be expressed in terms of other quantities. Okay, those are what are known as derived quantities. Now let's look at examples. We need to look at examples, of course. So what are those examples? When looking at derived quantities, we have examples like volume, okay, density. We have examples like power. We have examples like energy, pressure, refractive index. All these are examples of derived quantities. Now let's understand something here. Let's understand the system and units. So basically you have two types of systems used. Okay, there is one which is known as the international system of units. International system of units. So this international system of unit uses what is known as the metric system. And please remember that these are denoted as SI units. Okay, this uses the metric system. What is the metric system? It is just MKS. MKS. Now what does MKS mean? M simply mean a meter. So the SI unit for length is written as a meter. Then K simply means kilogram. S simply means second. So this is MKS, SI unit. So these are the units which were agreed upon globally, like to be used. Okay, so for length, SI unit is meters. For mass, it is kilograms, and for time is second. After you appreciate that, let's look at another system of units used. This is known as the British system. Now, what is it about the British system? This uses what is known as CGS. What is it about the CGS? C simply means a centimeter. So according to the British system, length is measured in its unit as centimeter, then mass in grams, and time, of course, in second. So this is basically the British system. Now let's look at some conversion of units. Okay, let's look at some conversion. So one thing you need to understand are these my simple conversion of units. For example, what is 1 inch? 1 inch, you must understand that 1 inch is equivalent to 2.54. Okay, it's equivalent to 2.54 centimeters. Then the other thing you must understand is how many miles make up, how many miles are able to make up a feet. So 1 mile make up 3 feet. Okay, let's understand another thing. How many meters make up a kilometer? Kilo means 1000, so it is 1000 meters. Then how many miles make up, let's say, a kilometer? So it is 1.609 kilometers. Okay, make up 1 mile. How many meters make up a kilometer? How many meters make up a centimeter? So it is 100 centimeters, which make up a 1 meter. This is very important concept for you to appreciate. Now let's look at an example. Let's say we want to convert. So convert let's say we have 50 inch to, let's say, what are you converting to? Okay, to meters. Let's do this. So we are converting 50 inches to meters. Okay, so how are you going to do it? So you write 50 inches there. So you use what is known as dimensional analysis. So you multiply, you always make sure that what you are multiplying with has a denominator of what is on the numerator. As simple as that. Okay. So you need to make sure that this is 15 inches, there should be inches there. Then you ask yourself, which first units can you convert to? Can convert to centimeters. We said that 1 inch make up 2.54 centimeters. Then again we multiply, because inch and inch will cancel. Then how many centimeters make up a meter? So we need to put centimeters there, then a meter on top. The exact unit we want is a meter. So 1 meter is made up of 100 centimeters. Of course, centimeter and centimeter will cancel, inch and inch will cancel. So we just need to multiply. Now, what is 50 multiplied by 2.54? Then divide by 100. So it is simply 1.27 meters. Okay, so 50 inch is equal to 1.27 meters. Let's have another conversion. Let's say you've been taught to convert, let's say, 25 meters per second to which units? Okay, let's say to which one? Okay, let's say mile per hour. We want to convert 25 meters per second to mile per hour. So we have 25 meters there over second. We multiply. You ask yourself, which first unit can we convert to? We can convert a meter first to to a what? To a kilometer. So we can say meter there down, then a kilometer on top. Then we ask ourselves how many kilometers make up a meter. So that is simply 1000. Okay, then we convert again. We want miles, so a kilometer will be at the bottom so that it will cancel. Then we ask ourselves how many miles make up a kilometer. So 1 mile is equivalent to 1.609 kilometers. Mind you, we are converting to how, but we have a second there. So you ask ourselves, we put a second on top, how many seconds make up and how? So 1 hour is equivalent to 3600 seconds. You need to understand that I've just multiplied what is 60 by 60, that is the seconds there. So second will cancel with that second, okay, meter will cancel with that meter, kilometer will cancel with that kilometer, will remain with the miles there, miles just, and a hour, which are the units we need. So we just multiply now. What is 25 multiplied by 1? That is 25 multiplied by 3600, that is just 3600. Then we have 90,000 there. So on the numerator we have 90,000. Of course we have miles over. Then on the denominator we have 1000 multiplied by 1.609, and that will give us 1609. So 1609, and this is in hours, not second. So if you divide 90,000 rather, divide by 1609, it is giving 55.9. Okay, we can end up to 4. That is mile per hour. Yeah, so that is how you can do the conversion there. Alright, so let's look at another thing which is quite interesting. Let's look at something interesting now after we've done these conversions. Okay, let's look at the scientific notation. So under scientific notation, this is just a way of expressing numbers in terms of powers of 10. Okay, it's a way of expressing numbers in terms of 10. That is scientific notation. For example, if you have 1000 can be expressed as 10 to the power 3 because there are 3 zeros. Okay, what if you have, let's say, 0.00000001? How can you express this number? So you can express this number as how many zeros? So we have 10, 1, 2, 3, 4, 5, 6. So and 7, so it will be 1, 8. Okay, for it to be 10. So we can say 10 to the power -8 because we are going to the right. Then on the same thing, we have what is known as standard notation. This is the same thing as scientific notation, but let's have a number like what is 2816.3 in standard notation. Okay, or in scientific notation. So for scientific notation, a number shouldn't be greater than 10. It has this formula. the scientific notation, this is the symbolic expression, that is a times 10 to the power n. Okay, and a should be less than 10. So let's express now this. How are we going to do it? So we're going to say this point to shift to the right 1 2 3, so it will come there, so it will be 2.8 times, okay, let me write everything. Okay, so 2.8163 times 10 to the power, how many values does it shift? 1 2 3, so it was going to the left, so it will be positive 3. Okay, so it's 2.8163 times 10 to the power 3. Okay, upon appreciating that, let's look at prefixes. So when I'm talking about prefixes, these are just numbers or the letters written at the beginning of a certain word. Those are prefixes. So in physics, we have what are known as multiples and submultiples. Okay, we have what are known as multiples and submultiples. So what you need to know is that for multiples, they carry a positive what index. For submultiples, it means that the number is too small. These carry a negative value. Okay, now let's look at multiples. Let's say, what is 10? What do we call a number? 10 to the power maybe 1. 10 to the power 1, this is known as a deca. But 10 to the power negative 1, it's a, this one is a what? This is a submultiple. So 10 to the power negative 1, this is known as a deci. Okay, what is 10 to the power 2? So 10 to the power 2, this is known as should be a hecto. Then 10 to the power negative 2, that should be a centi. Okay, then what is 10 to the power 3? 10 to the power 3, that should be a kilo. Okay, then 10 to the power negative 3, that should be a milli. Then what is 10 to the power 6? 10 to the power 6, that should be that is after a kilo, you have a mega. Okay, then 10 to the power negative 6, this should be a micro. And micro has that symbol, a mu. Then what is 10 to the power 9? Okay, 10 to the power 9, that is a giga. That should be a giga. Then 10 to the power negative 9, that should be a nano. Then what is 10 to the power 12? 10 to the power 12, that is a tetra. That should be a tetra, yes. Then 10 to the power negative 12, that should be a pico. Then what about 10 to the power, although they can't ask you this, let's just do it anyway. 10 to the power 12 is a tera, not tetra, sorry. This is a tera. Should be a tera, yes. Then what is 10 to the power? Of course, maybe there, in case 10 to the power 12, that is 24. I mean 10 to the power 24, that is a hecto. Then what is 10 to the power maybe 15? In case they ask you, you just tell them what that is a peta. Okay, that is a peta. Now let's look at something interesting here, which we are calling significant figures. Let's look at significant figures. So what are significant figures? These are just the numbers required when writing an answer. Okay, the numbers which should be obtained at the end of a calculation. The numbers obtained at the end of a calculation. So these numbers are very important because when you're given, let's say, give your answer in correct to this type of significant figures, they're able to determine the accuracy of your answer. Okay, now let's look at let's determine some significant figures. Let's say you have a number 1.3. How many significant figures do this number have? Okay, before we can do that, let me talk about laws of significant figures. Okay, or laws rather, significant figures. So one thing you need to know is that non-zeros are significant. Non-zeros are what? Significant. All non-zeros digits are significant. Number 2, zeros are not significant. But there are certain instances where these zeros will be significant. But basically, let's know that zeros are not significant. Number 3 you need to know is that leading zeros are never significant. Leading zeros are never significant. Not significant. I'll just be writing not sig. Okay? Leading zeros are zeros in front of a number. For example, you have 0.001. These zeros are in front of a non-zero digit. These are not significant. Then let's look at another example. Captive zeros. Captive zeros are significant. Okay? Captive. We have what are known as captive zeros. So what are captive zeros? Excuse me. These are zeros in between the number. For example, when you have 20001, these zeros are significant. Okay? But let's look at another example. What are another zeros we have? What are known as leading zeros? We have captive zeros. We have also zeros. What are they known? What are they called? Okay, I think my mind has misplaced it. But there are zeros after a certain number. For example, this 200. These zeros are after a non-zero digit. Okay, they are significant in some ways, but in a whole number, they are not significant unless there is a point they are significant. In fact, they are called trailing. Yes, these are these are known as trailing zeros. Okay, so trailing zeros are ever significant. When there's a point, and they are not significant when there is no point. Not significant. Okay, when there is no point. But let's now look at examples. Let's determine some significant figures. Let's say you have 2.4. How many significant figures are there? All 9 digits are significant. So 1, 2. So there are 2 sig figs. Okay. Let's have a number. Let's say 2,000 to 20,000. There's no point there. So all these zeros are not significant. There's only one significant figure. Let's have a number. Why am I writing all this? Okay, so let's have a number that's 4,000 with a point there. All these zeros will become significant because of the decimal point. So we have 4 significant figures. Let's have maybe 6001. All these zeros are in between the non-zero digits. They are captive zeros. We said captive zeros are always significant, so they are 4 sig figs. Let's have another example whereby you have, let's say, 20.100. All these zeros, these captive zero and these trailing zeros, because of this decimal point, they are all significant. So this number will have 1, 2, 3, 4, 5 sig figs. Okay. Let's have a number 0.00100. These zeros are not significant, but these zeros are significant. So this number, the point is where? The point is here, sorry. Okay, let me just clear it out. Okay, the point is there, it is 0.00100. So only these zeros are significant. So we have 3 sig figs. Okay. they won't ask you anything apart from that. What else do you need to know here? Okay, the other thing you need to know is rounding off digits. Rounding off. Okay, so how do you round off? The basic concept here, or the rules you need to understand, is that when you have a number which is less than 5, of course, for example, you have 2.34, then you are told to round off to 2 significant figures. Okay, when you are told to round off to 2 significant figures, you just say 2. We are ending on 3, 1, 2. There will be 2 significant figures, but 4 is less than 5, so this number will remain as 2.3. Sorry for that. So just be 2.3 because 4 is actually less than 5, so it won't add anything. It will just turn into 0, but don't add the 0 here because you'll make 3 significant figures. Then what if you have maybe 3 point another one? It's a rule which talks about numbers, let's say, greater than 5. So for greater than 5, let's say we have 2.65, and we're taught to round off to 2 significant figures. Okay, let me not use 5 because we'll come to it. 2.66, we are taught to round off to 2 significant figures. Okay, how can you round it off? So it will be 2. This, have you seen 6 where it is? This 6 which is proceeding is greater than 5, so it will drop a 1 there. It will be 2.7. That is correct to 2 figs. But let's look at the rule of 5. This is what is known as the rule of 5. So for the rule of 5, you need to understand something here. So for an even, don't add anything. Okay, if a number after that number where you're ending your significant figures is just 5, and that number, that preceding number, is even, don't add anything. Don't add a 1. Okay, but if that number where you're ending is an odd number, add a 1. Okay, let me give you an example so that this can be understood clearly, because it seems like it's confusing. So the first example is, let's say I have let me not use 2. Why do I like 2? 3.5 3.5650. Then you are taught to round off to 3 significant figures. Of course, 1, 2, 1, 2, 3. You need to end on 6 here. Obviously, the preceding number is 5, and this 5 there, that's where now the rule of 5 comes in. Can you see the preceding number? The preceding number is simply 6, so the answer will be 3.56. Don't add a 1 because this 6 is even. An even number can be divided by 2, so it is even. So don't add anything. But a situation whereby you have 3.615 and you're told to round it off to, let's say, 3 significant figures. Have you seen the number after 1? It is 5, so use the rule of 5. Now the preceding number is odd. This number 1 is an odd number. You can't say 1 divided by 2 to give you an exact value. No. So when you have 3.615, when you're rounding off, it will be 3.6. You add the 1 because 1 is odd, so it will be 3.62. So you only add 1 when the number after that value is 5 and when it is an odd number. Okay, so that is it. Then let's look at what is known as dimensions. We need to exhaust the entire topic, okay, in this session. So let's look at what is known as dimensions. So what are dimensions? These are just physical nature of quantities. Okay, nature of quantities. They are just physical nature of quantities. That is what are known as dimensions. Specifically now, let's look at dimensional analysis. Dimensional analysis. Now, what is dimensional analysis? You might be wondering, what is dimensional analysis? This is just the algebraic expression of dimensions for physical quantities. Algebraic expression of dimensions for physical quantities. Okay, let's make this interesting. Let's look at, for example, so the important dimension you need to understand are time. Time is represented as t. The dimension is t. Length, the dimension is represented as L. Then and also mass. Its dimension is represented by capital letter M, not small letter. Okay. Now let's look at the dimensions, for example, for density. What are the dimensions for density? We know that density is equal to mass over volume, right? But mass, the dimension is capital letter M. Then the volume is simply the amount of space, okay? And it is measured in what? Cubic centimeters. And the dimension for length, this is same as you've multiplied length times length multiplied by length for you to have, maybe this is in centimeter for you to have cubic centimeter. So simply we're going to say L to the power 3. So that is the dimension for density. Then let's look at for work. Okay, work, how do you find work? Work is equal to force times distance. Work is equal to force times distance, and this force also can be broken down into force is equal to mass times acceleration, then distance. Okay, multiplied by distance. And mass, we just said that the dimension is m. Then acceleration, you see, acceleration is the change of velocity over time. The change of velocity, that is in meters per second. Now over time again, so it will be meters per second square. So you're going to multiply mass, meters is length, sorry, then over second is just time, so it will be t square because of second square, then multiplied by distance. We are talking about length. So if they ask you what the dimension for work, the dimension for work is m. We are multiplying L times L, that is the L square, then over t square, over t square, over t square. But can you see that you can write this as m L square t square? You can convert this using just exponentials. It will be t, because it is at the bottom. It is at the bottom, so the power will be negative. So it will be t to the power negative 2. Okay. Okay, let me just write it properly. Let me just rub this part, then I write it properly. So it will be m L square over t square. So this can be written as m L square t to the power negative 2. So that are the dimensions for work. Now what's the importance of dimensions? Importance. So these dimensions help in determining the accuracy of the value. Okay? The accuracy of the value. We're going to prove that, don't worry. And it also helps in determining the consistency in units. Unit has to be consistent. So these are some of the importances. Now let's show how these dimensions can be helpful in determining the accuracy. There's this formula for period. The period is equal to 2 pi then square root of length over gravity. Okay, we know that period is just the time taken for a complete number of oscillations. That is the formula. Of course, you know, for period is equal to time over number of oscillations, but this is also a formula for period. Don't worry if you don't understand that. If you don't understand it at the moment, you just look for a video, then try to understand this. Okay, and how it comes about. So let us use dimensional analysis in order to prove this. Okay, so what are we going to say? We're going to say this. So we're going to say period is equal to this capital letter 2. So this is just a constant 2 pi. Then we have the square root. Length, the dimension is L. That's what we said, right? Yes, we said length, the dimension is L. Then this gravity is simply in meters per square second, right? So meters, it is L length over second square. Second square, the dimension for second, which is time, is t. So it will be time square. Let me just rub on top. So we want to prove this using dimensional analysis. So it will be period is equal to, it is 2 pi, then square root of L. So we have L divided by L over T square. Okay, and it will be equal to period is equal to 2 pi then square root this, the division, so we can find the reciprocal. So it will be L times this 2 will go up, then it will change to multiplication, then L down. So L and L can cancel. So what we are going to remain with is this, simply this. So it will be period is equal to 2 pi then square root of, so what will remain with is t square there. Let me rub this. So period is equal to 2 pi. We know that square root of t square, this power 2 will cancel with the square root, then we're just going to remain with t. But this is just a constant, okay? It's just a number. So we can say period is equal to period. So we've proved using dimensional analysis that there is consistency in these units. Okay, so let's look at something else. Okay, the last thing we need to look at, let me just give you another example. Let's find the dimensions for, what can we find now? For power. Okay, we know that power is the rate of doing work. So power is work over time. Okay, and work is force times distance, 9 over time. So force is equal to mass times acceleration multiplied by distance now over time. Then let's find the dimensions. Mass, the dimension is m. Acceleration, I think we talked about acceleration, and we said acceleration is simply the change of velocity with respect to time. So change in velocity, which is, okay, the units are meters per square second. Meters, it is, so it will be multiplied by meters, it's length multiplied by Okay, so let me just use the over thing, the division. So it will be L over second, it will be T square, then multiplied by, okay, multiplied by what? Distance is just L. Then we have time again, over time. So we can just say over T again at the bottom. Okay, over time, divide by time. Okay, so divide by time. So you divide by time, we can just say T at the bottom, yes. So this will be equal to M multiplied by L times L, that is L squared. Then at the bottom we have T square multiplied by T, that will be T to the power 3. Then what would be the dimension? So the dimensions now will be equal to M L square, then T, this will change, it is inverse, so it will be T to the power negative 3 since it's at the, it is on the denominator. So these are the dimensions for power. So we are done with this topic. The next part we'll do, in part 2 of the video, we'll just solve now exam questions on this topic. Thank you for watching. Have a good evening.